Hello everyone, myself Vedan Girish Shevle. I am from Aeronautical Engineering Department. So today our topic is ISA Activity 1 of subject Aircraft Structures. So our problem statement is a thin walled channel section subjected to following points. First is combined bending, that is phi and 4, that is mx and my. Then after that there is transverse shear force, that is 29, that is SY. Then after that there are two materials, that is aluminum and steel. So after that this is the diagram of the section we have given to solve. So in this there is a flange, there is a web, and there is a bottom flange also. So the given data it shows that the depth of the web is 25 centimeter, that is 250 millimeter. After that the breadth of the flange is 7 centimeter, that is 70 millimeter. After that the thickness is T is equal to 7 millimeter. So first of all we have to convert mx into kilonewton. It is in kilonewton meter, that is given, so we have to convert it into newton millimeter. So mx is equal to 5 kilonewton meter. So by converting it into newton millimeter, we got 5 into 10 to the power 6 newton millimeter. And same it is for my, and for sy we have to convert it into newton. The given they have is kilonewton, we have to convert it into newton. So that is 29 kilonewton that is given, and we have to convert it into newton. So 29 into 1000 is equal to 29,000 newton. Then after that there are some material properties of that two materials, that are aluminum and steel. So in aluminum, E is given as 70 GPa and G is given as 26 GPa. In steel, E is given as 210 GPa and G is given as 80 GPa. After that we have to find area. So for top flange, area 1 is equal to breadth into thickness. So breadth we have 70 and thickness we have 7. So area 1 will be 490 millimeter square. So after that bottom flange area will be 490 millimeter square, because of top flange and bottom flange are same, that is symmetric to x-axis. Then after that web area is given by d into t, that is depth into thickness. So we have calculated it as 1750 millimeter square, that is A3, area 3 of the web. So therefore total area will be equal to 490 plus 490 plus 1750, that is A1 plus A2 plus A3. So it will be calculated as 2730 millimeters. Then after that we have to calculate centroid location by taking bottom flange as a reference. So there are three parts: top flange, bottom flange and web. So by taking a bottom flange as a reference, we have calculated y, that is for top flange 253.5, for bottom flange 3.5, and for web 125. And we have also calculated area into y, that is for top flange 1,24,215, for bottom flange 1,715, for web 2,18,750. So as we have to calculate the centroid, that is y bar, so it will be equal to summation of ay by summation of a. So summation of ay will be all the summations of ay that we have seen before, and divided by that all the summation of areas. So by solving it comes to 126.3 millimeters. After that, we have to calculate Ixx. So for that, we have to calculate Ixx1, Ixx2 and Ixx3, and we have to add both of three. So for Ixx, we have the formula, that is bt cube by 12 plus a into y minus y bar to the power whole square. So by calculating this, we got Ixx1 is 7.92 into 10 to the power 6 millimeter to the power 4. After that, we got Ixx2, that is 7.38 into 10 to the power 6 millimeter to the power 4. After that, we got Ixx3, that is 9.11 into 10 to the power 6 millimeter to the power 4. So by adding all three Ixx, we got Ixx is equal to 2.44 into 10 to the power 7 millimeter to the power 4. So like this only, we have formula for Iyy, that is tb cube by 12. So by calculating it, we got Iyy is equal to 4.07 into 10 to the power 5 millimeter to the power 4. After that, we have the formula for bending stress, that is sigma z is equal to mxy by ix plus myx by iy. So we have y is equal to 253.5 minus 126.3, that is 127.2 millimeters. So for calculating bending stress, we will be putting all the values in the formula of sigma z. So we got sigma z is equal to 26.1 plus 9.83x, that is the equation for sigma z. So stress at extreme points of the flange, we have to calculate now. So half flange width is plus minus 35 millimeters. Then sigma is equal to, we have to put all the values of sigmas, all the values of x in the sigma equation. Then we will get the values, that is 370 MPa or minus 318 MPa. So for plus 35 we have put it, so it will be 370 MPa positive, and for minus 35 it will be minus 318 MPa positive, minus 318 MPa negative. So after that, shear stress due to Sy will be tau is equal to Vq by It. So we have Q is equal to A1 into Y, that is 490 into 127.2, that is 62,328. So we have the tau will be 29,000 into 62,328 divided by 2.44 into 10 to the power 7 into 7. So that is, we got 10.6 megapascal. So after that, we have to find a small q, that is Sy into q divided by I. So here tau will be q by t. So it will be, we have got 10.6 MPa. So for open channel section, the shear center lies outside the section. Then after that, we have to calculate strain. So for strain, epsilon is equal to sigma by E. So for aluminium, we have to calculate firstly. So for aluminium, we have seen the material properties, that is E is equal to 70 GPa, and so epsilon will be 26.1 divided by 70,000 MPa. 70,000 is a MPa that we have converted from GPa. So epsilon will be 3.73 into 10 to the power minus 4 for aluminium. And for steel, by the same method, we got 1.24 into 10 to the power minus 4. So steel experiences small strain because it is stiffer. Now we have the formula for curvature due to bending. So curvature will be denoted by K. So K is equal to M by EI. So firstly we have to calculate it for aluminium. So for aluminium, K will be equal to 2.93 into 10 to the power minus 6 millimeter to the power minus 7. And for steel, K will be, that is curvature due to bending, will be equal to 9.77 into 10 to the power minus 7 millimeter to the power minus 1. So steel curvature is 3 times smaller than aluminium. So shear flow will be like this. So it will be going like this. For the top flange it will be like this. For the bottom flange it will be like this, and for the web it will be like this downstream. So thank you.